The concept of antimatter has existed for almost a century now. It has dominated our sci-fi fantasies and spawned a number of theories. The holy grail of unlocking the mysteries of the universe, with little understanding of how it behaves. Or so we thought. Welcome to Synapse, a first-of-its-kind science, tech and society platform where we uncover the new within the now. Today, we're delving into the twin world of antimatter and how the latest research around it can help understand the universe with more clarity. But what exactly is antimatter? To understand antimatter, it is essential to first understand matter. Matter forms the building block for everything conceivable: stars, planets, us, and everything else in the universe. Matter can be broken down to its tiny particles, atoms with positively charged protons in the middle and negatively charged electrons revolving around it. Now imagine antimatter. As the name suggests, it's the opposite. Just like a mirror image, the electrical charges of the particles in antimatter are flipped. Antiatoms have negatively charged antiprotons in the middle and positively charged anti-electrons, or positrons, revolving around it. When matter and antimatter come into contact, they destroy each other, leaving behind nothing but pure energy. When the universe began, with the Big Bang, both matter and antimatter were created in equal measure. But today, even as we've observed trillions of galaxies across the universe, they're all made up of matter. It is extremely hard to come across antimatter. Where did all the antimatter go? But a new experiment has managed to demystify this twin particle, to some degree at least. This unexplained disappearance has continued to baffle scientists. Maybe antimatter behaves differently to matter? Scientists have recently proved that at least when it comes to gravity, antimatter responds to gravity the same way as matter does. Just like Newton's apple, antimatter doesn't go up but falls down. Over the last 2 decades, researchers at CERN have been using the Large Hadron Collider to create antiparticles, as well as the ideal conditions in which to observe them. Antimatter is notoriously unstable, so a big part of the job was slowing them down. They did this by putting them around a ring to draw out their energy. Then a magnet was introduced to trap the antiprotons and positrons, creating thousands of anti-hydrogen particles. But if the antimatter touched the container, it would get destroyed instantly. This is where the magnetic field came in handy, to keep them afloat. By controlling the force of the magnetic field, they were able to observe which way the anti-hydrogen went. And like all the greats, it fell. This discovery validates what Einstein had already claimed in his general theory of relativity: everything responds equally to gravity. This confirmation hasn't surprised anyone, but has opened up new doors for further experiments around the elusive antiparticle. The researchers are now investigating the nuances of how antimatter behaves in the presence of gravity. Dr. Danielle Hodgkinson from CERN explains that understanding this could reveal why our universe is matter-dominated. It's a big cosmic mystery they're determined to solve. The journey continues with the team at CERN upgrading their experiments to find even the tiniest differences in how matter and antimatter fall. In the meantime, this research, if nothing else, has shown us that the laws of nature are still firmly rooted to the ground. Thanks for joining us on this cosmic adventure through the twin world of antimatter. Be sure to like, subscribe, and hit that notification bell for more mind-expanding discoveries.